Alrighty, calculus students, we have a little mini lesson today on our last two derivatives that we're going to be learning for quite a while, and that is the derivative of e to the x and the derivative of ln of x. Okay, so I'm just going to start by showing a very quick example. We're going to skip over this bell work question, but we are looking at the derivative of e to the x. So on my calculator, I'm just going to use this to kind of explore what this looks like. I know what e to the x looks like. We've seen this before. So that is going to be an exponential function with my base as e. And what I'm going to do, this is something you haven't seen before, but if you wanted to graph a derivative of something, but you didn't know how to find the derivative, we have this nifty feature. I'm going to hit my alpha window button to pull up a little secret menu, and I'm going to go down to n derivative. And this allows us to request that the calculator take the derivative of something. So derivative with respect to x of, and you can either type in e to the x, or you can type in y1, since I'm going to have it find the derivative of the equation that I input in for y1. And this is like a when key, so we're asking the calculator to find the derivative with respect to x of y1 when x equals, and I'm going to put x in here because I want it to graph all of them. And when I hit the graph button, you can see my color changing, and it is sketching the exact same function on top of itself. Number for number, if I were to go to a table, number for number, oh, still graphing. Every single number in the column, 1, 2, 3, 4, those are identical. So that's just kind of a nice, easy way to see using our calculator that the derivative of e to the x is e to the x. It's the easiest derivative. It's the only function whose derivative is itself. So when you take a look at question number 1, we've got f of x equals e to the x minus 7x plus sine x. When we find our derivative, the derivative of e to the x is e to the x. The derivative of negative sine x is negative 7, not sine. And the derivative of sine x is cosine x. Okay, so that's pretty simple. So let's look at problems that have a chain rule in it. So we now have a function within a function. So my outer function is the e portion. My inner function is the 7x portion. So the derivative of f of x is, and the derivative of e to a power is e to the same exact power. You keep the inner part the same. But then I multiply by the derivative of the inner part, which is 7. So if anything, you can pull that 7 out to the front if you like. Take a look at example number 3. F of x equals e to the cotangent of x. So when you take your derivative of e to a power, it is e to the same exact power, but then I have to multiply by the derivative of the inner part. So the derivative of the inner part would be negative cosecant squared x. So if anything, I'll just pull that negative out to the front and bring everything else down. Example number 4 is actually very similar to example number 2. Derivative of e to the 3x to the fourth is e to the 3x to the fourth, but the derivative of the inside part is going to be 12x cubed. And so if anything, I would just pull that 12 out to the front. And we're all set. On number 5, we have a variable expression in the front times e to the 11x, which means we've got a little product rule here. So my derivative of f is f prime of x. I'm going to use first times the derivative of the second plus second times the derivative of the first. So first is x squared times the derivative of the second. So derivative of e to the 11x is e to the 11x times the derivative of 11x, which is 11, plus my second function, e to the 11x, times the derivative of the first function, which is 2x. And if anything, you could just move that 11 to the front. So 11x squared e to the 11x plus 2x e to the 11x. You could factor out an e to the 11x, but unless there's a purpose for factoring it out, at this point, you're fine exactly where you are. All right, last example, number 6. We're going to use our quotient rule here. So low d high, so low is x plus 2, d high, derivative of e to the x is e to the x, minus high, which is e to the x, d low, so derivative of x plus 1 is 1, all over the denominator squared. Okay, so when you're cleaning this up, you've got a few options. If you want, you could factor e to the x out to the front, or you could distribute it. This isn't so bad to distribute if you want to distribute. I'm a fan of factoring it out, so I'm going to factor e to the x out to the front, and that leaves me with x plus 2 minus 1 all over x plus 2 quantity squared. And I will go one more step. Let's see if I can squeeze this in over here. And I will just clean up x plus 2 minus 1 is x plus 1. And that is all over x plus 2 squared. Okay, we've got two applications down here. So find the gradient of the curve to y at x equals 0. Find the equation of the tangent line. Gradient is the IB word for slope. So that's just a fancy way of saying slope. So I'm going to start by finding my derivative. So that's a chain rule first. So I'm starting with my power rule. So 3 comes to the front. E to the x minus 5 carries down. Power drops down to a 2 times the derivative of the inner portion, which is e to the x. And now that's y prime. Now I want to substitute in 0 to find my slope exactly at 0. So 3 times e to the 0 minus 5 squared times e to the 0. All right, so as we're evaluating this, you will remember that anything to the 0 power is 1. So we have 1 minus 5, which is negative 4, squared is 16, times e to the 0, which is 1. So we have a slope of 48. We also need to find the point at 0. I know the x-coordinate is 0. We've got to find the y-coordinate. So I'm going to substitute 0 into my function. So e to the 0 minus 5 cubed. So that is 1 minus 5, which is negative 4 cubed, is negative 64. So now I have my slope. I have my point slope form. Y minus negative 64 equals slope of 48 times x minus 0. And there's our point slope form. Obviously, you don't have to write that x minus 0 at the end if you don't want to. All right, last question on this side. At what point on the curve y equals e to the x is the tangent line parallel to the line y equals 2x? Well, we know parallel lines have the same slope. So let's find the slope of this equation. That's in a linear form. So I know that's y equals mx plus b, so I know my slope is equal to 2. So I am going to find my derivative of this function, which would represent slope anywhere along that function. So that derivative is just e to the x. And now I'm looking for when that function has a slope of 2, so when the slope is equivalent to 2. So I'm going to substitute 2 in on this side. And I am solving a little exponential problem. We haven't done those in a while. When you have a variable up in your power, that's exponential. You could switch forms, or I'm going to take the log of both sides. So I always prefer to take the ln of both sides. So we would have ln of 2 on this side, ln of e to the x on this side. The reason why I like to take the ln is because I have a base e. And ln has an implied base e. With that base e, that simplifies. So my answer is x equals ln of 2. They asked at what point, so they might want a full coordinate. So I know my first part of the coordinate is ln2. If you are substituting ln2 back in, we would have y equals e to the ln of 2. That base e match. This simplifies all the way down to 2. So my points would be ln of 2, comma 2. Okay, that is the derivative of e to the x. Easiest derivative ever. Let's flip over to the other side. Let's take a look at the derivative of ln of x. So when you are finding the derivative of ln of x, our derivative is going to be 1 over x. But when you have a derivative that has an expression on the inside, that's an example of the chain rule. So if you were to apply your chain rule, it would still be the derivative of ln of x, which is 1 over x, times the derivative of f of x, which would be f prime of x. So One way that you can write this is f prime of x over x. Some people, there are different variations. I prefer not to memorize that it's f prime of x over x. I prefer just to know that I'm applying my chain rule. That way our chain rule gets applied the same way in every single type of derivative that we're finding. So take a look at example number 1. My outer function is the ln of x. The inner function is 3x. So for my derivative, the derivative of ln of 3x is going to be 1 over 3x. The inner part stays the same. So over here, you would have, oh, I'm just realizing, I'm so sorry. Over here, when we took the derivative of ln of f of x, the derivative of ln is 1 over x, but since that inner part is f of x, that would really be an f of x down here, my bad. So that would be f prime of x over f of x. I still prefer not to memorize that. I still prefer to remember to use the chain rule. But the inner argument here, that's called my log argument of x, will always stay the same in the denominator. So if it's something more complicated than an x, it's going to remain the same in the denominator. So over here, that's why when I take the derivative of ln of 3x, it's 1 over 3x, and then I multiply by the derivative of 3x, which is 3. If you look at example number 2, y equals ln of 2x to the 5th minus 3x, that is going to be 1 over 2x to the 5th minus 3x times the derivative of this inner part, which is going to be 10x to the 4th minus 3. So I'll just clean that up as 10x to the 4th minus 3 over 2x to the 5th minus 3x. There's an example on here of a product rule. I'm just going to skip around a little bit. So my first function is x. Derivative of ln of x would be 1 over x. Plus my second function is ln of x times the derivative of the first function, which is 1. So just to clean this up, x times 1 over x is 1 plus ln of x. And I'm hopping up here and I'm realizing we never simplified this one. That's what happens when we get really close to the bell ringing. Miss McInnes forgets stuff. The 3 and the 3 cancel out, so we have a 1 over x there. Okay, let's do one last example, maybe a quotient rule example. So take a look at example number 9. So we have low, which is x, d high, which is 1 over x, minus high, which is ln of x, d low, which is 1, all over low squared. So that would clean up to 1 minus ln of x all over x squared. And there are tons of other examples of these. You know, there are plenty. There's so many different variations of how this could be asked. But essentially, the derivative of ln of x is 1 over that log argument. And just remember, when you have an inner function, you've got to apply your chain rule. Okay, thank you so much for listening. And that's the end of our derivatives. Congratulations.